All right. Let's talk about coulombs. Okay, so Coulomb was an early French experimenter. Okay, and I discovered Coulomb's law, which you actually aren't going to take until next year. But basically, the Coulomb, the unit the Coulomb, is a measure of an amount of charge. Okay. So what do we mean by that? Well, let's talk about static electricity for a minute here. Let's imagine that we have an insulating material, and we rub that with another insulating material. Okay, this might be, say, a silk cloth, and this might be made of glass, for instance. If you do this, okay, what will happen is electrons will leave one of these objects and enter into the other one. Okay, so you can find a triboelectric series, which essentially is going to show you more or less what steals electrons from what. So if you take anything that's up here and you rub it with anything that's down here, electrons will move this way. Okay, this is the way that electrons will go. So they become positive and they become negative. So if you see silk is here, glass is here, that is going to indicate to you that silk will take some electrons away from the glass. And for every electron that gets taken away, that leaves behind a positive charge here and a negative charge there. So you get a stuck positive area inside this insulator and a stuck negative area inside of this insulator. The reason these hold charge and conductors do not is because as soon as you have an area of positive charge, well, electrons are going to flow down a conductor and just come in and neutralize. In an insulator, they can't do that. This is a little bit of a review from what you've taken before. Okay, this is one way of charging objects. It's by rubbing. They call it triboelectric charging. So charging by rubbing similar objects together. Okay. A little bit more background on this whole thing. Electros is the Greek word, or at least the historical Greek word for amber. This effect was first kind of noticed by Thales in ancient Greece when he had an amber collection, I guess, and he was rubbing and cleaning his amber collection and noticed that amber was capable of storing up a big charge. Okay, so he wrote about that later on when Enlightenment area scientists were studying the same effects. They went back to this old Greek word and used electros, meaning amber, to describe this. So electrons, electricity, and so on come from the Greek word for amber because of ancient Greeks polishing amber. So there you go. Now, the reason we would say here that silk takes electrons away from the glass is that silk has a higher electron affinity. Now, that's like a chemistry word. It means something a little bit different. I mean, it's a similar idea in chemistry, but yeah, it means how actively electrons are pulled away. So things that become negative have higher electron affinities. So in this case, rubber and Teflon have a very high electron affinity, and things down here have low electron affinity. Now we're talking about the classical view of charge here, maybe not sort of the actual true electron view of charge, but you don't need to worry about that too much, okay? So we're just going to worry about the fact that every electron that leaves here means this gains a bit of negative charge, and this loses an equal amount of negative charge. So that also leads us to understand that there is a conservation of charge in materials and in nature. No new electrons are being created and none are being destroyed. We're just moving them to different spots. All right? So conservation of charge. Nothing new is made in this process. Okay. All right, let's just review conductors and insulators. So conductors, metals tend to be conductors. So let's think about what a metal is like. So we've got a metal, and metals are made up of atoms like everything else, but their atoms are a bit different than the atoms of nonmetals. So the plus signs here are going to represent atomic nuclei, okay? And the metal sort of forms like a crystal type of structure where these are like joined together, but they're joined in a strange way. So their inner shells are locked. You remember like your Bohr model idea? You've got your nucleus, then you have your like um, shell levels. And we know that inner shells are stable, right? And then the outer shells have valence electrons. And it turns out the way that metals work is the inner shells are locked and stable, but these outer valence shells have electrons that are sort of more or less free to move about within the metallic structure, okay? So if I were to take an electron and push it in this end of a conductor, there'd be a repulsion, right? Like charges repulse. So these electrons would repel all the way along, and one would be able to like pop out the other end. This also explains some of the properties of metals. Most of them are malleable. So if you think of a metal as sort of like a bunch of positive islands, and then there's a sea of electrons around that are attracted to all these positive charges around here, but they're not like rigidly bonded. It makes sense that you'd be able to bend something like this because these electrons can sort of just reshuffle themselves and keep this thing kind of like attached together. It also explains the conductivity of metals as well as ductility. So you can draw metals out into thin wires without them breaking. And that's sort of this gluing effect of these valence shell electrons. Now let's look conversely at insulators. Okay. So insulators are non-metals or things like plastics and rubbers and so on. Generally, like organic substances tend to be insulative, and the reason why is because rather than being like a crystalline structure of metal or like metal, where electrons are kind of capable of like moving around, and there's sort of this fluid essentially within there. Um, these tend to be rigidly bonded to atoms, right, in molecules. So if it happens to be like some sort of polymer plastic, for instance, you get this long chain of bonded electrons. All the electrons are involved in bonds for the most part, right? So you don't get the ability for electrons to like flow along. So if I put one in here, it might like feel a resistance to this electron here, but this electron is locked within a bond and can't cause the same kind of flowing of charge that you would get in a conductor, okay? So insulative materials, they tend to, although not always, well, they're non-metals. It's not they tend to be. They are. Okay, all metals can conduct to some extent. So they're non-metals. And there's a wide variety of things that end up being insulators, but a lot of them tend to be made of like polymer or large molecules. Okay, now what happens when we charge an insulator? Well, I take this, insulated rod here, ebonite or whatever, and I rub it with, say, some fur. Okay, well, what you might have here is, yeah, so what you might find here is, originally, before we do any charging here, the fur and, this plastic rod here have an equal number of protons and electrons, and therefore they're both neutral, right? There's always, in every atom, there's an equal number of protons and electrons. You do some rubbing here, all right, and some electrons are going to leave the fur, and they're going to end up popping in here, and they're going to be extra, and whatever left here, we're going to leave behind a positive charge there, okay? Now, these electrons can stay charged and can stay in this spot when we remove the fur because they have absolutely no way to escape. They can't just leap off into the air. Air is an insulator. To their left, they've got insulated material, so this charge is stuck there. Call that static electricity. If you did the same thing here, you pumped in some extra electrons, well, all that's going to happen is they're going to like flow off, and if this is connected to a ground, they'll go into the ground. Now, if this is insulated from the ground, we'll talk about a ground in a minute, but if we say put it on like insulating blocks, like a couple blocks of wood, then you can actually charge up metal with static electricity. You just have to make sure you don't touch it because you'll ground it, or you don't attach it to the ground because you'll ground it. Okay. Whereas I could, I could have my hand at the end of this thing. Okay, there's my hand, and charge cannot be pushed off of here and into my hand. Whereas here it could, right? If I put my hand on here, I'm going to receive those electrons, and this will be neutralized. Okay, does that make sense so far? That's kind of a review, I think. And then let's talk about this concept of grounding. So once something's charged, we can ground it, which is the same thing as neutralizing it. Okay, so let's imagine we have this scenario, and we have this extra bit of charge over here. If I touch this with my finger, what will end up happening is these electrons, due to the fact that they repel, right? Like negative charge repels itself, they will come into my finger, and I am acting as a ground. So what a ground is it's a large body, or the earth itself. So large body or the earth itself. Okay. That is acting like an electron reservoir. Okay. It can give or take I'm going to put an infinite sign. Like, we know it's not really infinite, but it's just such a large number, it might as well be infinite. Infinite electrons. Okay, and the symbol we use to say something is hooked up to the ground is this like upside down antenna symbol. A way to protect your house would be to put a lightning rod on top of it, right? So if you have a lightning rod, the idea is if lightning's to strike, it might strike the lightning rod and take that charge down under the ground, right, and spread it out within the earth. So you might have buried metal plates under the ground attached to this wire, and that's where that symbol comes from. It looks like metal plates buried under here. Little insider secret, though, is that if you have a lightning rod, your house won't get struck by lightning because it actually serves to neutralize your house rather than attract lightning to it. Or so I've heard. Actually, we can do a little experiment with that later. And you can actually see that a pointy metal object actually like blows excess charge off of it. So it's kind of interesting. But anyway, this is the ground symbol, and I'm pretty sure it comes from the way that lightning rods work. Okay. Okay, so let's talk numbers. So let's imagine here that we have two spheres. Okay. And these are both metal spheres, and let's say they're insulated from the ground. And let's say that we charge this with +1 Coulomb. I'll talk about what a Coulomb is in a minute. And we charge this with 4 coulombs. So for a total number of coulombs of 5. And then let's say we touch them together. If we touch them together, what will happen is the charge, because they're metal, will evenly flow. We touch them together, and the charge will distribute itself such that each ends up with, say, 2.5 coulombs. Now, in reality, dealing with amounts of coulombs this big is quite unrealistic. So what is a coulomb? A coulomb is an amount of charge, and it's equal to the charge on 6.24 times 10 to the 18 electrons or protons. If you have a collection of this many electrons, the cumulative charge of all of them would be 1 Coulomb. Okay. So then we can say that E, the elementary charge, the charge on one electron, it's called the elementary charge. It's the smallest charge possible with normal matter. Elementary charge should be equal to, if you have this much making 1 Coulomb, you can say I have 1 Coulomb for every this many electrons, then each electron must have 1.6 times 10 to the negative 19 coulombs of charge. Okay, so that's E, the elementary charge. It's 1.6 times 10, and that's negative 19. It's a little bit hard to see. Let me fix it. Just do this. Negative and 19 coulombs of charge. And proton also carries that amount of charge. It's just that it is positive on a proton and negative on an electron. Don't ask me what positive and negative necessarily mean. They are just opposite properties of electrons and protons. Okay? Now we also know this. Like charged objects repel, okay? Unlike charged objects attract. Okay, so we're going to imagine that we have a ball here, and we're going to say we removed some electrons from it. We took them out. We took electrons out of here. What we're going to say then is it's no longer neutral. It's got positive charge. So I'm going to give it a positive charge sign. Now, we're going to talk about the concept of electric fields. Sometimes electric fields are drawn with this curly E, okay? Sometimes they're drawn just as E. Really depends, okay? Now we are going to take what is called a test charge. A test charge, and test charges are always positive. And we're going to move it around this central positively charged object, okay? Now we said that like charges repel. So we're going to think about wherever I put this test charge, it is going to feel a force in some direction, right? So if you think about it, because it's repelling, I could take it and move it anywhere in here. No matter where I move it, it's going to feel a charge away from the central charge. So what we'll find is as we move it around, we get this sort of concept of the electric field pushing out of positive charges, okay? And the reason why that happens is because we always test fields with a positive test charge. So you remember with gravity, right? Gravity was always attractive. Electric fields can be attractive or repulsive, and they work on kind of like different principles. So where gravity works on mass and is a property of mass, electric fields work when you have charged objects, and they're a property of charged objects, okay, versus massive objects. So you can probably kind of use your head here and think what will happen if I bring my test charge near a negatively charged object. So we put a bunch of negative charge in here, okay, and then I bring my little test charge. Remember, test charges are always positive. Well, this is going to be attracted into the negative charge no matter where I put it. So we're going to have this kind of a scenario going on. Okay? So you need to remember that. Test charges are positive, and I can draw fields based on them. Make sense? Okay, now what's going to happen if we have a positive and a negatively charged object and they're nearby each other? Let's think what would happen if we put our test charge right in the middle here. That's our test charge. We would expect this to happen. It would just be repelled from the positive and attracted to the negative. Okay? If we say took our positive test charge and put it over here, It's going to be repelled from the positive, attracted from the negative, but it's much farther away from the negative. So it's going to overall just have a push away over here. Okay, if I put it over here, it's going to be attracted this way, right? Our positive test charge, because of its proximity, right? These fields get weaker just like gravity does the farther away you get. But now the interesting question is, well, what happens if I move it to some different spots? If I put it really close to this object anywhere, it's going to more or less point straight out of it, right? And if I put it really close to here, it's going to more or less point straight in. If I put it kind of in the middle, well, it's going to be repelled from that one and attracted to that one. And by vector addition, we're going to get that. So we're going to build up, using our kind of logic and intuition, what this field would probably end up looking like. So you're going to get a repulsion there, an equal vector there, and an attraction there. And you're going to get the same thing here. And depending where you go, you see this pattern start to like build itself up. So you get these field lines that kind of look like this when you have two charged objects close to each other. Okay, so that's kind of the pattern that it's going to make. Now, how do we know this? Well, from experiments and from tests, right? And also from logic. Now, I'm drawing this in 2 dimensions, but in reality, if I had 2 spheres in space, this would be a 3-dimensional electric field here, right? So these lines are representing direction of force, a positive test charge, or really any positive charge, would experience at a given point. Okay, so let's say we took our test charge and we placed it like right here, and we just measure. We put a scale on it and we saw where the force pointed. Well, the force would point always tangent, right? Tangent to the field line. Wherever we put it, it's always going to feel a force tangent to the field line. Okay, so at this point, it's pushing away. The reason why, it's closer to this, so it's the push away from here is greater than the pull towards here, but there's a little bit of a pull towards here. Okay, does that make sense? So these lines are showing the direction that you'd feel at a given instant here, right? In the middle, you always feel this, your positive test charge. And by the way, what if we switch this to being a negative charge? What would change about the force? The direction would just switch, right? So like, oops, let's say we took a negative charge and we plopped it like right here. Okay? Well, if it were positive, we'd get an arrow pointing that way. But if it's negative, we get just an arrow pointing in the opposite direction. Okay, so the other thing you could probably have here, or possibly have, is you could have a situation where these are charged the same. Now, if I take a positive test charge and I put it right in the middle here, I think about what forces are going to be active on it. It's going to be repelled from that and repelled from that. And if we add these 2 vectors together, they're going to cancel each other out. And we're going to have no force in the middle. If we bring it up here and up here, you have this crisscross with that, add them together tip to tail, and you get just a straight upward force. So I'm going to draw in the field and see if it makes sense. And here's something that's really going to help you to visualize this. Imagine that these are wind sources and wind sinks. So you can imagine wind blowing out of positive and sucking into negative. If 2 winds are both blowing towards each other, those winds are going to collide and they're going to like bend off. Okay? They're going to bend off. So in this scenario, you have like an area right in the middle where there's no field lines because they've canceled one another out. And this wind analogy really helps you to make sense of what's going on. Okay, the 2 winds are blowing into each other. In this case, a wind is blowing out and a wind is blowing in. So yes, that makes sense, right? The wind is going to curve in. Now, what would happen if I just flip-flop these both to negative? What would happen to my field? Nothing. The only thing that would happen is these arrows would switch direction and they would be drawn inward rather than outward, right? It's like we're now sucking wind into these things and you get this sort of a scenario. Okay, last thing here. Let's talk about electric field strength. Can I get off this orange color? I'm tired of looking at it. Electric field strength. All right, so let's, in order to try to make sense of this, let's think about gravitational field strength first. Gravitational, that's a hard word to spell for some reason. Field strength. So we measured that in how many newtons we got, right? So let's say we have a mass here. We measured the strength of a gravitational field above, say, a planet or a moon or a comet or the Earth as how many newtons of force every kilogram of mass experienced, right? That's how we talked about the gravitational field strength. So at the surface of Earth, we get 9.8 newtons of force towards the Earth for every kilogram of mass we put there, okay? It just so happens that this, right, remember this is a kilogram meters per second squared, that's the unit for newtons, times the per kilogram, well, they cancel off, and it also works out to be the same units as acceleration, right? But what I want you to think about is this way, the newtons per kilogram, how many newtons per kilogram? And I want you to like figure out or think about how are we going to measure if we have a charged object, we'll make it negative to kind of make it similar. We know the field lines are pointing in, right? And remember with gravity, they were always pointing towards the center. Okay, that's what the field lines looked like with gravity. Now we have this electric field. We'll use a curly E. This is maybe not the correct symbol. This is a symbol that our workbook uses, so we'll just keep it that way. Don't sweat it. Okay, that's just electric field strength. If gravitational field strength is working on mass and it's measured in newtons per Coulomb, what do you think electric field is going to act or work on? The amount of blank per blank. So people are telling me I misspoke. Gravitational field is newtons per kilogram. This, by analogy or by similar concept, is now going to be how many newtons of force we get per Coulomb of charge. Newtons per Coulomb of charge, right? A stronger field, which we would get by putting more negative in here, means we get more newtons of force for a given amount of coulombs. It's like if I went and stood on the surface of a much more massive planet or a much more dense planet, the gravitational field strength would be stronger. If I take my charged object near something with much more charge in it, well, the field around it would be much stronger. So units are newtons per Coulomb. So how do we write that out? Well, we say this. Force on this object is equal to Q times E. Or another way to say this is the field strength is equal to the force felt per given amount of charge. So let's just define these things. So this is field strength, and that is measured in newtons per Coulomb. This Q represents charge. Charge is measured in terms of coulombs, and this is force measured in our old friend newtons. Okay? And so if we know the field strength, we could say for every Coulomb I'll get this much charge, or sorry, this much force. Or I could say if I have this much force for this many coulombs, I must have a field strength that's this strong. So here I'll write a little problem and then we'll wrap her up. Okay, so a 2 microcoulomb test charge. And by the way, in real life, a coulomb is an absolutely incredibly huge amount of charge. Normally, like if you charge yourself up with socks on the floor type of thing, you're not transferring more than about a microcoulomb of charge, okay? Yeah, yes, it's something to the power of 18 electrons, which is like an insanely huge value, okay? So anyway, 2 microcoulomb test charge is placed in a 10,000 Newton per Coulomb electric field. Find F sub E, that's going to stand for the electric force, on the charge. Okay, so this is pretty straightforward. Fe equals the amount of charge we have times our unit for field strength. So in this case, we have 2 times 10 to the negative 6 coulombs times 1 times 10 to the 4 newtons per coulomb. Negative 6 plus 4, negative 2, 2 times 10 to the negative 2, cancel off coulombs, newtons of force will be felt. And so the question is, what does this look like? All right, so here's our charge. Here's our field. Here's where we put our test charge. I'll put a T there. Now, if it is a positive test charge, that force is in this direction. If it is a negative test charge, that force is in this direction. And it's this amount of force. And that's where we'll stop.